All right, here's my video guide for lesson 6.1.3, talking about how can I prove it. And so what we're going to do here is prove the triangle congruence conditions we talked about in lesson 6.1.2. The first two we're going to prove is going to be side angle side and angle side angle, and we're going to do that through using rigid transformations. And what we can do is say that if we can get the one triangle to land on top of the other only using rigid transformations, we can prove that they must be congruent. Because remember, rigid transformations, they preserve side lengths, they preserve angles, so we're not changing the shape at all. And so if it lands exactly on the other one, they must be congruent. They must be the exact same. All right, we did something similar to this when we were doing similarity. We said if we could get one triangle to land exactly on the other using rigid transformations and dilations, then they would be similar. By cutting out dilations, because dilation is not a rigid transformation, so by cutting out dilations, we can then use this same kind of idea for congruence. Okay, so in the first slide here, what you're going to notice is we are going to do this. We're going to try to move this triangle ABC on top of DEF, and we can do that using our student e-tool, but what I want is you to read the story and read how this team breaks down and how this team models the idea of communicating how we're going to do this. Okay, so we're gonna read the story here, and then we're going to perform the operations, the rigid transformations that they are telling us to see if it's going to work. And so we see here that Jurgen says that we know that congruency means that two triangles have the same size and shape, so we have to be able to move the triangle ABC right on top of DEF using only rigid motions because they preserve, again, lengths and angles. So how can we do this? Well, Carlos chimes in and he says, well, we can certainly move A on top of D with a translation to get a new triangle A prime, B prime, C prime. Now, when they say a new triangle, it's going to look the exact same, but we're calling it A prime, B prime, C prime because we performed a transformation. We slid it over, and so really it's a new triangle. It looks the exact same, and so we're calling it A prime, B prime, C prime, and then that new A point, A prime, is going to land exactly on top of D. Okay? Then Mary Sue added, oh, then we can rotate A prime, B prime, C prime about that point D and get A double prime, B double prime, C double prime with A double prime, B double prime pointing in the same direction as DE. So again, they're now saying A double prime, B double prime, C double prime because a second transformation took place, a rotation took place. And so again, it's a new triangle. Even though it looks exactly the same, it's a new triangle, so we denote it by using those primes. Okay? Then we're saying that this line AB needs to point in the same direction as DE. And then it says, but does this point B double prime land on top of E? Well, Emmy said, sure, we know that rigid motions like translations and rotations preserve angles and lengths, so AB equals A prime B prime equals A double prime B double prime, right? And since we are assuming that AB equals DE, then A double prime B double prime should equal DE, meaning that AB is the same thing as A double prime B double prime, and so if this one equals, the other one should equal as well, okay? And so really it should work out that A double prime B double prime C double prime, or after we perform these rigid transformations, it should land right on top of the other triangle. And so now we get to try it out in our student e-tool, and what we do, like they said, we're going to bring A onto D, and then this would technically be triangle A prime, B prime, C prime because we performed one transformation. Then we're going to rotate about point D here so that AB is laying in the same direction as DE, and if I do that, so those two are lined up, you can see that it lands right on top of each other, just like they said it would. So I like that problem because, again, it models what good team conversation can be. It models how we can brainstorm different ideas to try to make something work. All right? In this next one, in kind of the last part here, it says, what about these triangles here? How can we make them coincide? So you're going to discuss what the previous strategy was, and then you're going to click on this e-tool, and you're going to try to get this triangle to land on top of the other one. Okay, the rigid transformations may be different, but I still want you trying to discuss and model, base your conversation you're going to have on the model you see here, and determine what's the right course of action here to make this happen. And then explain in the box below why this proves that all triangles with this side angle side congruence must be congruent. Okay? Then moving on to 4, same kind of thing. We have now to prove angle side angle triangle congruence, and it says that when you prove side angle side congruence, you found a sequence of rigid transformations that moved one triangle onto the other. And we're going to do a similar strategy here for angle side angle. So suppose that these triangles ABC and DEF, where AB equals DE, angle A equals angle D, angle B equals angle E, as shown at the right. Now you're going to use the student E tool and perform rigid transformations that move the triangle ABC onto DEF. And then you're going to list the transformations you used and explain how this shows that the triangles must be congruent. Okay? And then I want you to explain how this shows that all triangles, and think about this too when you answer this question, that how generic this triangle is with no side lengths. But then explain how this shows that all angle-side angle conditions are congruent. Okay? Now, here's a really interesting thing, and it even says so. Interestingly enough, each of our triangle's congruence conditions can be shown to be true by using either angle-side angle or side-angle-side. So we just showed that side-angle-side is proven to be true, and angle-side angle is proven to be true. So we're going to turn side-side-side, angle-angle-side, and hypotenuse leg into either angle-side angle or side-angle-side, because those have now been proven. So if we can transform these to these two, then we can say that they must work as well. And so the first one's the toughest one, because we need to show that angle A equals angle D, because then we can say that these two must be congruent using side angle side, and that must mean that all sides could do the same exact thing. So in this one, it even gives you a hint, you need to use the law of cosines. And I'm going to show that here, and I'm going to show how this works. Okay? So what I'm going to do is I'm going to first label my sides. The one with the 1 tick mark I'm going to call A, 2 tick marks I'm going to call B, and 3 tick marks I'm going to call C. And since they are side triangles, this 1 tick mark is also A, this 2 tick mark is also B, and this is C. So writing law of cosines equations for the first triangle, I'm going to say I have C squared equals A squared plus B squared minus 2 times A times B times the cosine of angle A, because angle A is my angle right here. All right. Now I can write a law of cosines for the other triangle, so that is C squared equals A squared plus B squared minus 2 times A times B times the cosine of angle D this time. And you can see these triangles, the equations for law of cosines look very similar, which already leads me to believe that angle A and angle D are the same. But what I'm going to do is I'm going to solve the equations for the cosine of angle A and see if I get the same thing for the cosine of angle D. So what I'm going to do, I'm going to subtract over A squared, subtract over B squared, and I'm going to divide negative 2 times A times B. So what that gives me here is I'm going to have C squared minus A squared minus B squared from subtracting those over, divided by, that whole thing divided by negative 2 times A times B, and that all equals the cosine of angle A. Now, if I do the same thing to the bottom equation, I'm going to get the same exact thing. And so I'm not even going to rewrite it because it just takes too much time and I don't really feel like it. All right, so I'm going to get that. This is what I would get if I subtract over A squared, I subtract over B squared, and I divide it over negative 2 times A times B. So this cosine of angle A also equals the cosine of angle D, which tells me that if these cosines are equal to one another, that angle A and angle D must be the same. So it has been proven here now that this angle A and this angle D are the same, and then you have side angle side congruence. We proved side angle side congruence early on, so that means side will always work for us because you could do this with any side congruence triangles. Okay, kind of interesting, kind of weird, but I like that they put these together and use what we proved earlier, to come back here and help us out for side. Now we're going to prove angle side. This one's a little bit easier. And what we can do here is, we can say, if these two angles are the same, that means this third angle must be the same by the triangle sum theorem. And if this third angle is the same, then it becomes an angle-side angle congruence, which we proved earlier. So that one is really quick and easy. By being able to use the triangle sum theorem, we get to find the third angle. They should be the same, and it becomes angle-side angle, which again we proved earlier, so that means it's going to work, and it would work for any angle side. Lastly, we have hypotenuse leg, and we talked about this one in class. Think again Pythagorean theorem. If we call this A, and we call this C, and we call this A, and this C, because they're the same length, then if we find what B is, using the Pythagorean theorem, we should be able to say, okay, this becomes then side, angle, side, and we would have our congruence there. I want you to think about that one, write out an explanation about how this would work. I did it a little bit in class for 612, so I kind of want you to explain how this can work by explaining how the Pythagorean theorem connects that these missing sides B and B would be the same, and how we could end up then having a side angle side congruence. All right, that's it for this lesson. Again, we discovered these 5 congruences, and here we're proving them, and so now we can use them anytime we want to prove that 2 triangles are congruent.